Welcome back to Analog Electronic Circuits. This is the fourth lecture, and today we are going to discuss start making circuits with MOSFETs, and we hope to make our first amplifier circuit using a MOSFET. So, in the last class we were a brief recap of what we had done, and we looked at the characteristics of the MOSFET in the last class. And in the characteristics of the MOSFET, we found that there is a triode region which we do not like, and there is a flat region of the MOSFET which we like, and we are going to operate the MOSFET in its flat region as far as most analog circuits are concerned. And in this flat region, the behavior of the MOSFET is like a voltage controlled current source. The flat region works out when VDS is more than a certain voltage, it should be more than approximately VGS minus VT. Okay. If you are in the flat region of the MOSFET, then ID changes only with VGS, and this relationship goes by ID is equal to k times VGS minus VT the whole squared, okay, where k is some arbitrary constant as of now. K, actually we know what k is, but let us not worry about it. So, this is what we did in the last class, and then what we did was we applied VGS and VDS on both sides of the MOSFET, and then we applied an incremental small voltage VGS and a small voltage VDS, and then we did a Taylor series, right. ID was some function of VGS VDS, then ID plus small ID is going to be the same function of VGS plus small VGS VDS plus small VDS, and then we did the Taylor series. The full Taylor series breaks up into partial derivatives, and we ignored the higher order terms because small VGS and small VDS are really small. Okay. And then what we got was that the complete current is equal to the constant current at the operating point plus a slope times VGS plus another slope times VDS. We modified that to say that the small current, the incremental change in current is equal to a slope times VGS, the incremental VGS plus a slope times the incremental VDS. Okay. So far so good? Yes. And then what we tried to do was to interpret this equation above in terms of a circuit, and this is really crucial. Understanding this is absolutely crucial. We did this in the last minute of our last lecture. So, I really want to make sure that you understand this. This is an equation. I am trying to represent this equation as a circuit, all right. So, what I have done is ID is the sum of two currents. So, it is the sum of two currents, this one and this one, KCL. Okay. The first current is dou ID by dou VGS times incremental voltage VGS, dou ID by dou VGS times incremental VGS. The second current is dou ID by dou VDS times VDS, right. If the voltage between these two is VDS, then this current is going to be VDS divided by the resistor. The resistor is 1 by dou ID by dou VDS. So, it is really dou ID by dou VDS times VDS, that is the current. Okay. Now, you had a question, your question was why is this a resistor and this a current source? Why not both current sources, or why is this not a resistor? Why not both resistors? Okay. So, the answer is that this particular path, this side is D, this side is S, the current through this path depends on the voltage between D and S. So, that is a resistor, whereas here the current through this path does not depend on the voltage VDS, it depends only on VGS. So, this is not a resistor, this is a resistor. Okay. Is this understood? All right. So, the model is clear. Now, we have some shorthand notation for all of these, we are going to present some definitions over here. So, our first definition is going to be GM, this is going to be called the transconductance. This is defined as dou ID by dou VGS, and this is a very important parameter. Okay. Remember, dou ID by dou VGS is significant, dou ID by dou VDS is very small, the slope is very small, right. This is taking into account a slight slope in the characteristics. If there is no slope, then nothing happens over there. Okay. This particular slope over here is very small. So, in a very good MOSFET, the slope will be 0, right. That is what the analog circuit designer wants. So, to the analog circuit designer, dou ID by dou VDS is going to be a small number. The resistance between D and S is hopefully very large, because it is 1 by. Okay. So, some people call this GDS, some people call this GO, right, and this is called dou, this is dou ID by dou VDS, right, and if you like writing it as a resistance, okay, you can call it RO or RDS. So, these are just definitions that we are going to stick to. Remember, GM is very significant, RO is hopefully very large, it is a large resistance, GO is hopefully very small, GDS is very small, GM is something significant. Okay. So, analog circuits, we worry about GM a lot. All right. So, our model now does not need these complicated equations. So, between gate, drain and source, our model is, I have got a voltage controlled current source of value GM times VGS and a resistor of value RO or RDS, whatever you want to like to write. Okay. And I have labeled the terminals in small letters, right, because this circuit is not the actual circuit, this circuit is only the incremental circuit. So, with this circuit you will be able to work out only small I small d, right. This current is not the complete current, this current is only small I d, fine. So, this is called the incremental small signal model of the MOSFET. And if you have studied the BJT, if you are coming from the BJT world and watching this video, then the model is slightly different. In the BJT world, you arrive at a hybrid pi model. So, over there it looks like this. Okay. So, this is the extra one R pi, and this current source is beta times I b, base emitter collector, and this is some large resistance, right. Usually you do not worry too much about this resistance in the BJT, it does not matter, but it still is there just like RO. So, this resistance is there. All right. So far so good. Okay. So, this is not really, the BJT is not really part of this course, but I am just trying to point it out. If somebody is already familiar with the BJT, then where am I in that perspective. Okay. So, what we have done so far is we have applied voltages, we have incrementally changed these voltages, and we have worked out a circuit representation of the incremental change in the current. And let us see how we can work with this forward. So, let us say that I have a MOSFET, okay, and suppose this voltage is at VGS plus some incremental voltage. So, this is ground, right, this terminal is ground. So, I am not going to worry about it. Source is at ground. So, instead of writing VGS, I am writing VG plus a small Vg I have applied at the gate. And what is this in terms of our convention? It is small sub capital. Small sub capital is capital capital plus small small. Okay. Now, source is constant at 0 volts. So, this is going to cause a current I d plus an incremental change in the current, which is small I d. As a result, what is going to be the voltage over here? Just by the way, the voltage over here was capital V d plus an incremental voltage small v d, but if you look at the circuit, this current is I d plus small I d. Suppose this resistor is R, then what is the voltage here? So, the voltage over there is equal to V d d minus okay. So, let us call this R d. Is this okay? All right. Now, if small v d was equal to 0, suppose this small v d or rather small v g was equal to 0, all of this small incremental stuff was 0, then you take away small v g, take away small I d, right. What is capital V d then? Capital V d would just have been capital V d d minus capital I d times R d. So, this is the absolute voltage over there. So, this is this V d, which means that small v d is nothing but minus I d times R d. Okay. Look what happened. I first applied just a constant voltage V g, I obtained a constant current I d, I obtained this current I d and this I d flows through R d, and that automatically means that the voltage at the drain V d is nothing but V d d minus I d R d. Okay, you have a question. The question is that the voltage at the drain depends on I d, but the voltage at the drain is also controlling I d, right, in a weak sense. Yes. Okay. So, let us assume that you know how to do that. I am going to show how to work it out just now, but let us assume that you know how to do that. In that case, V d, capital V d is just V d d minus I d R d. The incremental change in V d, when I applied an incremental voltage V g over here, it created an incremental current I d, and that created an incremental change in voltage V d. So, that incremental change is nothing but minus I d R d, and this is coming from KCL and KVL, nothing else. Okay. So, I am not really looking at any functions, okay, or any slopes or what the device characteristics is. I have not seen all of that. This is coming just from KCL and KVL and from our definitions. Okay. So, what this could lead to is as follows. I had the incremental model of the MOSFET, which created an incremental current. Okay. This was the incremental model of the MOSFET. I applied an incremental voltage V g over here, right. It created some incremental currents I d. This incremental current is going to flow through the resistor and come from a voltage V d d, but incrementally the voltage V d d is not changing at all. So, the incremental change in V d d is nothing. So, this is going to be treated as a ground. Okay. And lo and behold, you have got 0 volts, you have got minus I d R d over here, and this was the drain voltage. Okay. Do you see that it is working out properly? You think it is fluke? No, it is not. Think about it. This is what we have done is precisely correct. There is no ambiguity in this. All right. Now, let us go back to your question. I have applied a voltage V g over here. Okay. Now, V g, if the device is in its flat region, I do not know whether it is really in its flat region or not, but whatever it is, there is going to be some current I d. The voltage over here is going to be V d d minus I d times R d. Okay. Now, so far this is from KCL, KVL, actually no KCL, only KVL. Okay. The voltage over here is V d d minus I d R d. This is coming purely from KVL. So, suppose I draw a graph and on the graph I make the x axis as V d. By the way, V d is the same as V d s because source is at 0 volts. Okay. On the y axis I place I d. Then how is this going to look? V d is equal to V d d minus I d R d. How is this going to look? This is going to look like a straight line, right. This is the equation of a straight line. V d is the x axis, I d is the y axis. This is the equation of a straight line. Straight line which cuts the x axis at what point and y axis at what point. So, if I d is equal to 0, capital V d will be equal to V d d, and if V d is equal to 0, then I d will be equal to V d d by R d. And then beyond that, this is nothing but a straight line. You have no choice about it. Okay. This is coming only from KVL, nothing else, and KVL is always correct. So, this is a straight line. We have not yet worked out the device over here. Now, I d is also happens to be a function of V d because of the device. The device has some responsibility to play. I d is going to be a function of V d, and what is that function? Depending on the value of V g that you have chosen, you are going to pick a curve, and the curve that you have picked depending on the value of V g could be this, and if it is this, then V d and I d have to satisfy KVL, which means it has to lie on the blue line. It also has to satisfy the device characteristics, which means it has to lie on the red line, which means that V d and I d have to be this point, this intersection point, and that is it. That is the only V d and I d choice that you are allowed to have over here, which satisfies both the blue line from KVL as well as the red line from the device characteristics. Okay. If the device had if this red line had some slope, so be it, there is still going to be only one point of intersection. Okay. Now, what we are going to do is we are going to change V g. Let us apply a small incremental change to the gate voltage. If I incrementally change the gate voltage, I will have to incrementally select a new curve for this red line, for this device line. So, the new curve for the device line, let us mark it in red again. Okay. What about the other the blue line? Will the blue line change? No, the blue line never changes, right. Whether you have changed I d or not, right, I d can change with time, but if this current changes, no problem, you will still have to adhere to the blue line. The blue line is coming from KVL and nothing else. Okay. So, whatever is that current, you still have to adhere to the blue line. So, when I incrementally change the gate voltage, I would have to shift to this point over here. If I pull the gate voltage down, I will have to shift to a third point. right. Depending on which way I incrementally change the gate voltage, I will be changing my drain voltage. So, suppose I incrementally change my gate voltage, then my drain voltage will also change incrementally. Okay. So, for example, suppose I incrementally had a sine wave riding on top of the DC gate voltage. Then correspondingly I would have a sine wave of small I d amplitude, which is riding on top of capital I D. So, this if this has an amplitude of small v g and this has an amplitude of small I d, then I d is related to small v g by I d is equal to this slope times v g, okay, g m times v g. This slope is g m. Okay. Very good. Now, that I need to select different lines over here, right. I know which lines I d is changing by. So, accordingly I need to select 3 different lines, and accordingly also depending on the slope of this curve of this blue line, I will get notice when I d increased, the drain voltage decreased. So, I drew the sine wave over here like this. For here I pointed the sine wave in exactly the opposite way. So, this sine wave is going to have an amplitude V d, and that is okay. Why? There is a slope on this line. What is that slope? Yeah, that slope is R d minus R d. Yeah. Okay. So, is this does this answer your question? Okay. So, this so far what we have done is assuming that the slope of the curve in the flat region, the slope is very large, that is what we have assumed so far. But if I do not assume that the slope in the flat region is very large, then this calculation is going to be a little hard. Okay. It is not going to be so straightforward. So far it is good, V d is equal to minus I d times R d. Okay. But I need to figure out what is this I d, small I d. Small I d happens to be a function both of V g as well as V d. So, it is not very obvious what is the relationship between I d and V g, because had it been a completely flat thing, a completely flat region, then ID small id would depend only on small v g, small id would be g m times small v g, but not anymore. Okay. Now, we have small id is equal to g m times small v g plus g o times small v d, or in other words I can redraw my circuit in this fashion. Okay. VDD does not change incrementally. So, I have marked this as nothing 0 volts, when you do not write the value of the voltage it is 0 volts. The ground terminal is fixed, it does not change incrementally. So, this is also marked as 0 volts. Then the resistor remains a resistor, all the linear elements remain exactly where they are. The MOSFET is going to be replaced by its small signal incremental model, which happens to have G m times V g and R o. Fine. And then I just work out what happens. I applied a V g over here, okay. It creates a current G m times V g. This G m times V g current happens to split up between R d and R o. R d and R o appear in parallel to each other, right. So, the voltage V d is equal to minus I d times R d parallel R o sorry, this current times R d yeah, it is not I d times R d parallel R o anymore. I d is the sum of these two currents, right, but this current is G m times V g. So, G m times V g times R d in parallel with R o, whatever that is. Is that okay? Yeah. So, this is also correct, but this is also correct. This is not I d, this current is not I d, this current is I d. Okay. So, be careful over here. So, this is correct, this is also correct. So, it is G m times V g, that is the current, and this current is going to come through a combination of R d and R o out of the ground terminal, 0 potential terminal. So, combination of R d and R o is R d parallel R o, and you know what that is R d times R o divided by R d plus R o. I do not want to write it down. Okay. So, that combination resistor is carrying a current G m times V g. So, the voltage that appears at the drain terminal is minus G m times V g times R d parallel R o. So, V d is equal to minus G m times V g times R d parallel R o. Now, this is the incremental change in the voltage. All right. Now, let us look at a scenario where R o is very, very large, because the device is in its flat region, and let us suppose it is a good device. So, R o is infinite. So, R d parallel R o is approximately R d. G m is a large number, right. Suppose it is a large transconductance. Just to give you an idea of what large is, 1 millisiemens could be a good value for GM. 100 kilo ohms could be a good value for RD, okay. In which case 1 millisiemens and 100 kilo ohms combine, multiply with each other, and you get 100. Okay. So, 1 millisiemens, 100 kilo ohms Vg. So, Vd by Vg is equal to minus Gm times Rd parallel Ro, which is approximately Rd, minus Gm times Rd. Rd is 100 kilo ohms, Gm is 1 millisiemens, will give you minus 100. What does this mean? This means that if small Vg is 1 millivolt, then small Vd is minus 100 millivolt. Okay. You have successfully made an amplifier. You applied a small signal worth 1 millivolt and the response at the drain was worth minus 100 millivolts, right, 100 times larger. Okay. So, this is the function of an amplifier. All right, this is your first amplifier, just by the way. It is not complete, this amplifier is not even close to complete, but at least you are seeing that with the help of a MOSFET you are achieving some sort of amplification. That is what we wanted, right. This is the crux of the course. Okay. Making an amplifier is the objective of this course, because once you can make amplifiers, you can make all kinds of other circuits. Okay. So, Vd by Vg has come to a large number, right. I have just thrown in some numbers, Gm is 1 millisiemens, Rd is 100 kilo ohms, and that automatically gives you Vd by Vg to be equal to minus 100. And this amplification is very nice. This is exactly what we want. If I apply 1 millivolt signal at the gate, I get a response of minus 100 millivolts riding on top of capital Vd. Okay. So, let us understand. Go back over here. I started with a voltage Vg, right. This was my voltage Vg, and then on top of the voltage Vg I applied a small signal small Vg. Okay. So, this is that small signal that needs to be amplified. The capital signal does not need to be amplified, that is known as the operating point of the MOSFET, of the device. Okay. So, the operating point is capital sub capital always. The signal that needs to be amplified is small sub small, that is the signal. So, I have the operating point plus a small signal, right, that creates, the operating point creates an operating current, it is called the bias current, plus a signal current small id. Select the line depending on the current, right. This is the operating point capital Vd plus a signal voltage small Vd. Okay. And what we are saying is that this small Vd is 100 times larger than small Vg. So, if I apply 1 millivolt over here, I will get minus 100 millivolts over there. So, I apply 1 millivolt sine wave, I get minus 100 millivolts sine wave. But this sine wave is riding on top of the operating point. Is this so far understood? Okay. So, this is our first amplifier, and amplifiers unfortunately will all have this operating point. They are not going to operate around 0 volts. Okay. So, we have two businesses over here. One is, the first thing that we need to do is, I need to work out how to set an operating point. Such that device is in its flat region. Why is the flat region important? Because RO would not have been large had it not been in the flat region. If it was not in the flat region, this RO would not have been large, it would have been rather small. You know, you placed 100 kilo ohms plus a small resistor would have been the small resistor, right. So, this large gain, this large amplification that you got was primarily because you had a large resistance RD over here in parallel with a very large resistance RO. Now, if that very large resistance is no longer large, then that is going to dictate the value of RD parallel RO, in which case you are going to find out that this amplification factor is not going to be significant at all. Okay, it is going to become rather small in fact. GM is also going to change, but most important is this region. RO needs to be very, very high. So, that is why I want the flat region. Okay. So, this is something that I need to work out. I need to figure out how to set an operating point, or rather how to create an operating point, how to establish an operating point. And then number 2 that I need to do, I may or may not need to do this, is to decouple the signal from the operating point. Okay. This is the second thing that I need to do. What I mean by this is the fact that over here my output was riding on top of the operating point. I do not want that. I want the output to be just the signal. I want the input over here, the input was a small input riding on top of the operating point. I do not want that. My small input is just going to be some small signal. That is what I really want. Okay. So, these two things I need to work out. First, I need to work out how to set an operating point, and the second I want to work out is to decouple the signal from its operating point. Okay. And once I understand how to do these two things, I am all set. Okay. So, the first part, how do I set an operating point? The operating point is the current capital ID and the voltage VDS. The current capital ID and the voltage VDS, these two comprise the operating point. Okay. Sometimes you want to have a clear idea of what is the value of ID and what is the value of VDS. You also want to establish a voltage at the gate. Okay. So, One simple way to establish a voltage at the gate is with the help of a potential divider. So far we have been using a voltage source. Unfortunately, these voltage sources are not that easily available, right. Battery is always of a fixed voltage. So, you have to get your you have to create these voltages out of the same old battery. Okay. So, you have got one battery, let us say the battery is 1.5 volts. So, from that 1.5 volts you have to create the desired value of Vg, which I might be able to do like this. And then once I have created the desired value of Vg, I can apply okay. I can work it out like this. So, now I have a desired value of Vg, source is at 0. So, Vgs is established, and from the curve, from the MOSFET curve, Vgs ID as a function of Vgs, I work out what is ID, and the voltage at the drain is going to be VDD minus capital ID times RD, and that is going to be equal to VDS. Okay. So, this is the straightforward way of doing things. Unfortunately, this is not very good. Why is this not good? Any idea why? Why would I mean this is very easy. I set the value of gate voltage that I want, and automatically the current is set, and then from that I work out what is VDS. Why this is not good is because the relationship between the gate voltage and the current is very sensitive. The current is not sensitive to drain voltage, but it is very sensitive to the gate voltage as long as you are above Vt, right. In fact, it goes up as a square, right. So, if I make a small mistake in choosing the right value of the gate voltage, then I am going to be off by a large amount. If I am off by a large amount, suppose I have underestimated the value of Vg, I have applied a slightly larger Vg than required. If I applied a slightly larger Vg than required, then Id is a lot larger, it is very sensitive, right. If Id is a lot larger, then Vds happens to be a lot smaller, and remember Rd is something that you want to be large. Okay. So, the same phenomenon that gave you the gain in the amplifier, that same phenomenon is at work over here. A small error in choosing the value of Id is going to create a large error in Vds. In other words, a small error in choosing the value of Vgs will create a large error in choosing the value of Vds, just like earlier, right. Earlier I applied a small signal of 1 millivolt on Vgs, I found that Vds is 100 millivolts smaller than its DC operating point. Here if I make an error of 1 millivolt at Vgs, then the error in Vds is minus 100 millivolts, it is 100 millivolts smaller than it should have been, and that is not good, because that might break your circuit. Your Vds has to be more than a certain amount. Remember, right, Vds has to be more than a certain amount, it might break things. This is for flat region, right. To remain in the flat region, VDS has to be more than VGS minus VT. Now, if you say that a small error in VGS, 1 millivolt error in VGS has created a 100 millivolt error in VDS, then are you sure if VDS is correct or not? You are not sure anymore. Okay. So, that is the reason why this establishing the operating point in this fashion is not really very nice, it is not good at all. Okay. The same phenomenon that gave you gain in the amplifier is working against you over here in creating the operating point. All right. Then what do we do? So, one strategy is to do something like this. Okay. Now, what is going to happen? What is the voltage here? It is the same as earlier, right. It is a potential divider. I have a voltage over there. Okay. And then the source voltage is no longer at 0, all right. So, this is the critical thing, the source voltage is no longer 0. So, this voltage is VDD times R2 by R1 plus R2. The source voltage is VGS less than the gate voltage. Okay. So, Vs is this gate voltage minus VGS. VGS can be written as something more than Vt. So, this is what we write it as. Okay. This is called the gate overdrive. So, this entire thing is VGS, fine. This is the gate overdrive. This VGST is shorthand, instead of writing VGS minus VT, we write it as VGST. Okay. So, this is my source voltage. The current ID is Vs by Rs, but it is also the same over here. Fine. So, now what you have to do is you have to work out an equation. Your equation is going to look like this. So, I know the gate voltage, okay, and the source voltage is the gate voltage minus Vt minus VGST, VGS minus Vt. Okay, this is the source voltage. This source voltage divided by Rs is equal to ID. But VGS minus Vt, that is VGST, okay, this VGST is also related to ID through the device equation, and the device equation says that ID is k times VGST, VGS minus Vt the whole squared. Okay. So, in other words, you write this and now you need to solve a quadratic equation to arrive at the value of I d. Okay. So, you can crank your quadratic skills and arrive at the value of I d. What we are going to do is we are going to stop over here and discuss from this point onwards later on. What we have covered in today's class, first we started with the model of the MOSFET, and then we showed how we can get amplification if I operate in the flat region of the MOSFET, right. That was our first so called amplifier, but it was a very crude amplifier because I was unable to figure out how to set the DC operating point, and I was unable to decouple the input and the output signals. So, then we started working on creating the DC operating point, and yeah, so that is where we are. So, our first circuit did not really work because the same principle with which we did amplification, the same phenomenon which gave us amplification created an error in the DC operating point, and therefore, that is not a very good way to set the DC operating point. So, this is the second thing that we are working on, and then we have arrived at a quadratic while working on this circuit. We arrived at a quadratic, and this quadratic needs to be solved sooner or later. Okay, thank you.